Yes, hello everyone. My name's Neville Palmer. Yeah, Margaret, as Margaret mentioned, I formerly, many years ago, it was the Merchant Navy, not the actual Navy, not the Royal Navy, but the Merchant Navy. But I was a radio officer in the Merchant Navy, and now I teach computer networking. But I still maintain interest in amateur radio outside of that, and that's what I'm going to talk about today. There's just an event that happened. It's one of those interesting historical events that happened. So there's a bit of history in it, but also the current sort of state of play, how we're gathering data. You know, there's a lot of data there. So if you're interested in data science, there's a lot of data there to be explored that's being gathered at the moment. And actually, as I speak, my own transmitter is banging away, sending out some of that data, hopefully around the world. So I'm going to start my presentation. So I'll share the screen. I'm going to mute my video whilst the video is playing, but I've got a video with it, and I'll answer questions afterwards. If you can't hear the sound, just give us something in the chat as well. So I'll just start playing it now. Hello, my name's Neville Palmer, and I'm going to talk about radio propagation from no data to big data. This talk was inspired by an event that happened 100 years ago this December, which is being celebrated at this moment. It involved reception of high-frequency radio signals from across the Atlantic, which started a step change in our understanding of radio propagation. And as we moved forward to today, we can use prediction software, and we can also use digital transmission techniques. And we can also automate the data gathering process, which helps us to improve our research into propagation and solar activity. In 1900, people knew very little about radio propagation. And they believed that transatlantic wireless was actually impossible. However, Marconi disagreed. He'd been conducting a number of experiments, and the range of his radio transmissions were slowly increasing. And he noticed that he thought that range could be extended even further. So in 1901, Marconi built a transmitter at Pole 2 in Cornwall. Now, the transmitter power was only about 10 to 12 kilowatts. It operated on we believe about 500 kilohertz, although he didn't actually measure the frequency at the time, but it was somewhere just below the current medium wave band. The antenna that he used was a 50-wire fan stretched between two 61-meter masts. The original antenna consisted of 20 masts, and that fell down in a large storm. He had a lot of problems with bad weather at the time. So Marconi and his assistant Kemp went to St. John's in Newfoundland to set up the receiving station to receive signals from Pole 2. And this wasn't the site they'd originally planned, but they had problems with the antennas and bad weather, and they settled on St. John's in the end, and they set up a kite receiving antenna. Now, on the 12th of December, during the daytime, they received 3 Morse code dots, which represents the letter S, and that was the signal from Pole 2. However, there's some controversy as to whether they actually did receive the 3 dots or whether they just imagined it, because we now know that on medium frequencies, such as 500 kilohertz, propagation between the UK and Canada isn't possible during the daylight hours. But what we believe may have happened is that Marconi actually received the signal from Pole 2 on a harmonic of the Pole 2 transmitter on a higher frequency, because the signal from transmitters weren't very clean in those days. And we'll hear more about that perhaps later on. Now, Heaviside in the UK and simultaneously Kennelly in the United States looked at Marconi's work, and they thought that Marconi's Atlantic signals must be, the range must be due to an unseen reflective layer in the upper atmosphere. And this was named the Kennelly Heaviside layer in their honour. and that was in about 1902. In December 1902, a full year after the first tentative letter S had been received from Pole 2, the first full message from a station at Glass Bay in Nova Scotia was transmitted to Pole 2. And following further tests, a full commercial radio system was established between Clifton in Ireland to Glass Bay in Nova Scotia in 1907, and further tests and improvements were made following that. And in 1909, Marconi was jointly awarded the Nobel Prize for Physics for his work. Now, a station was built by the Marconi company at Carnarvon in Wales. It was a transatlantic station in 1916 with the call sign Mike Uniform Uniform. It consisted of a 1200 metre antenna fed by 36 wires, and it was powered by a 200 kilowatt transmitter. That was actually considered low power at the time, believe it or not, but it operated on a very low frequency of 21 kilohertz. The wavelength was actually 14 kilometers. That frequency is about 14 kilometers. So the ideal antenna length for a quarter wave antenna would have been about 3.5 kilometers. So the antenna was actually quite small in comparison to the wavelength. But this was for two-way transmission between the UK and the Canada and USA. So there was an experiment set up in Sydney in 1918. A guy called Edward Fisk. He built this quite large antenna in his back garden, and he was able to receive the first wireless messages direct from the UK from the Carnarvon station. And that was on the 22nd of September 1918. But the signals were weak and were only audible at certain times. Now, interestingly, the UK transmitter, although it was 200 kilowatts, which sounds a lot of power, the Germans had a more powerful transmitter, and in fact the Australians were regularly able to receive that throughout the war, in fact. But Amalgamated Wireless Australia, which was actually part owned by Marconi, the Marconi company, they built the first direct two-way low-frequency wireless communication system to the UK. Now, during the First World War, all amateur experiments had to cease. But in 1919, amateur radio activity was allowed to resume. But they were allocated what was thought to be the commercially useless frequencies below 200 meters, or 1500 kilohertz in terms of frequency. That's towards the top end of today's medium wave broadcast band, and they were restricted to a maximum power of 1 kilowatts in the USA. Most did operate close to the 1500 kilohertz. At the time, it was believed that the only reliable means of propagation was using the ground wave, and the lower the frequency, the greater the range of the ground wave. That's why it was that the Carnarvon station, operating on the very low frequency of 21 kilohertz, was able to reach Australia. So at a frequency of 1500 kilohertz, the ground wave was very much less than that, and that's why these frequencies were thought to be commercially useless. And of course, the radio amateurs saw that they got shorter range on higher frequencies using the ground wave. But it was also difficult to transmit on the higher frequencies using the equipment at the time. But some of the amateurs, especially in the United States, noticed they got considerably longer range at night time and in winter. And they asked the question, would it be possible to span the Atlantic even at these frequencies? And they wanted to find the answer to that. Now, to place that into some kind of perspective, it's like expecting a little low-powered local radio transmitter, like this one near Hythe, which operates with a power of about 500 watts on 1557 kilohertz, and normally serves just Southampton and the New Forest. It's like expecting that to be heard from the United States. It would be a tall ask even today. So in February 1921, the UK amateurs listened for 25 active US transmitting stations, but nothing was heard, and they put it down to the fact there was just too much interference. At the time, the receivers were so crude that they actually caused interference to each other, and you can imagine in the confined sort of environments of the UK where you've got a lot of stations, maybe in London, for example, the receivers actually caused interference to each other, so they believed at the time. So in November 1921, the Amateur Radio and Relay League, which is the organisation which represents radio amateurs in America, the call sign 2ZE to the UK. Now he was an expert radio systems engineer. In fact, he designed a transmitter that was used during the First World War in the trenches on the Western Front. But he came over in the SS Aquitania, and he had the assistance of the Marconi company with some of the experiments. And he went to Ardrossan in Scotland because this was a fairly quiet location. He brought with him the latest super heterodyne receiver, which had just been designed by a famous guy called Armstrong, and used this Beveridge antenna. Another guy called Beveridge had designed this antenna. It was a 1300 feet long wire antenna. So on the 12th of December 1921, there was some success. He heard reception from US amateurs, and he received some special codes that they would use to confirm reception, and they sent it via the Marconi station at Carnarvon in Wales to the United States to confirm reception. But what of two-way communication? Obviously it's no good having one-way communication. There needed to be two-way, so that's from the United States to the UK, and UK or Europe to the United States. But in France there was somebody called Leon Deloy, 8 Alpha Bravo, that's his call sign. He used the shorter wavelength of 100 meters. That's about a frequency of about 3 megahertz. And he easily made two-way contact with the United States. And the finding was that shorter wavelengths and higher frequencies give greater range more reliably, with less power, and with smaller antennas, because at the shorter wavelengths the antennas were shorter as well and smaller. So those useless shortwaves weren't so useless after all, were they? So Marconi in 1923 and 1924, aboard his yacht Electra, he conducted some shortwave tests at sea, and they were successful. Now he'd been asked to open these very low frequency stations on behalf of the UK, but instead they opened this beam wireless service for the General Post Office, and he first opened the service from Bodmin in Cornwall to Canada in 1926 on shortwave, or high frequency as we call it. But in 1927 they were able to establish a service between Bodmin and Australia, again on high frequency. So they needed to use high gain directional antennas on higher frequencies, and they could use lower power. So all the low frequency high power stations were scrapped. They didn't need them anymore. Now in 1924 medium wave broadcasting had started in the UK in about 1921-22, but this guy called Edward Appleton at the Rutherford Labs noticed that medium wave transmissions from Bournemouth, there was a little medium wave transmitter at Bournemouth, about 1 or 2 kilowatts in power, but the signal was constant during the day, but it faded up and down at night. So he worked out there must be two paths, but he proved by measurement that there's a sky wave that refracts the signals from an unknown layer, but he later called this, it was later called the E layer. And he found also that higher layers are responsible for long-range propagation, and they were called the F layers. And he realised that this was due to these were ionized layers in the upper atmosphere. So the upper Earth's atmosphere had been ionized by solar radiation. And he used high gain directional antennas to beam signals off of the ionosphere to measure their height and reflectivity, etc. So he was actually awarded the Nobel Prize in 1947, it turns out, for his work. And so Heaviside and Kennelly were actually proved right. Interestingly enough, actually, the method of reflecting radio waves from the ionosphere, this method was later used by Watson Watt to invent radar, which was of course used to great success during the Second World War. Now, propagation prediction is the sort of science of predicting which frequency would be best to transmit a signal between 2 points on the Earth at any particular time of day. So this is important if you're using high frequency short waves to send messages to Australia. You need to know the best time of day to actually send them and the best frequency to use as well. So the data to support propagation prediction was slowly gathered by observation over a number of years, and it was found to vary due to the time of day, whether it was midday or whether it was late at night, for example, due to season, whether it was winter, summer, spring or autumn, due to the distance, whether it was just a few hundred miles or thousands of miles, and the frequency, whether it was a lower frequency towards the lower end of the high frequency spectrum or towards the higher frequency end of the high frequency spectrum, and also due to, of course, solar activity. And this depended on sunspots and the sunspot cycle, the activity. This varies every 11 years. We're currently just past the minimum at the moment. And of course the solar wind has some effect. And solar flares, we get them occasionally, they can be disruptive to HF communications as well as satellite communications incidentally. So how can we predict radio propagation conditions? Well, today we can use propagation prediction software, but how do we improve its reliability? Well, I'm going to show you how you can use data gathering techniques, big data, to inform the research into propagation and also into solar activity. Of course, when computers were developed, people started to look towards using software to predict radio propagation, and particularly when the PC came along, of course, the IBM PC. The Voice of America produced some software. The Voice of America being the American National Broadcasting System for overseas shortwave broadcasting in the United States, broadcasts in many languages around the world. They produced this VOACAP software, this is you can use this to predict propagation, and it now uses a digital mode gathered by radio emitters called FT8. For example, it uses the 20 meter or 14 megahertz amateur band, and it monitors stations in various parts of the world, and at different times of the day on particular frequencies, and it uses that information to be able to predict which frequency will be best at any particular time of day, at any particular time of the year, day or time of the year. And for example, here's an example of the VOACAP data from FT8 data for 2018. So this is the whole year of 2018, and this is on a frequency of about 14 megahertz. And here you can see that during the daytime, this is over a particular path. Not sure which path this one actually is, but this is signal strength received at various times of the day. And you can see that in wintertime there are some gaps where there's no signal at all during hours of darkness. But in the summertime, where there's more solar activity during the daytime and even nighttime, where nights are shorter, of course, you'll see there's some activity on that frequency of 14 megahertz during the nighttime. 14 megahertz is about in the middle of the sort of high frequency spectrum, what we call the HF band. And if we want to predict a particular path, so this is say the UK to Australia on the short path, because there is a long path, you can actually go over the South America and via the Pacific Ocean in that direction, or you can go over Asia, as you can see here, towards Australia. So this short path is over Asia. So this is a propagation prediction table from the UK to Australia, over the short path that is over Asia. Now if you look at the left hand side, you can see these are the bands. These are amateur radio bands in meters, and along the bottom row you can see these are times in 24 hours. Now looking at the bands, you've got the 10 meter band at the top there. That's approximately a frequency between about 28 and 30 megahertz. The 12 meter band corresponds to a frequency of just below 25 megahertz, and the 15 meter band is about 21 megahertz. The 17 meter band is about 18. The 20 meter band is about 14 megahertz. 30 meter band is about 10 megahertz. The 40 meter band is about 7 megahertz. The 60 meter band is just above 5 megahertz. And you've got the 80 meter band between about 3.5 and about 3.8 megahertz in this country. Now, incidentally, if you look at, say, the 10 meter band, a half-wave dipole on 10 meters would be about 5 meters, whereas a half-wave dipole on 80 meters would be about 40 meters in length. So obviously, the higher the frequency, the smaller the antenna. Now, what we're looking for in this sort of table here is we're looking for a bright orange color to give us the best signal and the most reliable conditions. Yellow is almost as good, not quite as good. The sort of blues and greens are not as good again, but still reasonable reliability, and the greys are the least reliable, poorest signal conditions, but there's still a chance of getting through. So the best sort of band here is the 12 meter band. You can see at about 0900 hours, where there's a bright orange square there. The 15 meter band seems to be reasonable between about 1200 and 1400 UTC. And then the 17 meter band seems to be pretty good between about 14 and 1500 hours. There's still a good chance on the 20 meter band between about 1400 and 1700. The 30 meter band's not quite as good, but there's a good chance between, say, 1700 and, say, 2200 hours. The 40 meter band's not as good again, but you've still got a chance between 1600 and 2000 hours. And on the 60 meter band, there's not quite as good a chance, but you've got a chance around 1800 hours of making contact. And it's not predicting any communication conditions at all for the 80 meter band. Incidentally, remember the 80 meter band of about 3.5 megahertz. Leon Deloy used the 3 megahertz band to communicate with North America, but that was at night time, and the path was only 3,000 miles. So it's a bit different proposition when you're trying to communicate with Australia over this long path where it's sort of maybe 11,000 miles. But that's propagation prediction, UK to Australia. Now, another way of viewing similar data is to look at the optimum traffic frequency for the time of day. Now, so you want to find the most reliable frequency for communication. This is between UK and Australia again, and if you look at the column which says REL, that's reliability, and if you look down to where the red line is, you'll see that 81% reliability corresponds with the time in UTC over the left hand side of 0900 hours. And if you follow it across, you've got a column there which is labelled FOT. That's frequency of optimum traffic, which is 19.6 megahertz at that time of day. So they reckon that that's the best frequency to use. You've also got a maximum usable frequency. You've also got a suggested frequency, so you could try one of these 3 bands at that time of day. And if you follow it down, if you look down the reliability column again, you'll see that again at about 1500 hours, there's a 79% reliability, and that's using a frequency of optimum traffic of about 15.2 megahertz. So there might be more than one time and one frequency during the day which conditions are pretty good. They seem to be pretty good between probably about 0800 and about 1600 on various bands throughout the day. And now we'll look at this guy here. This is call sign Kilo 1 Juliet Tango, Joe Taylor. Now, he won the Nobel Prize for Physics. He discovered a new type of binary pulsar at Arecibo Radio Observatory in 1974. Now, this is where a lot of professionals are engaged in radio communications, and he also developed a number of weak signal digital communication modes. And obviously the work that he did at the Arecibo Radio Observatory sort of helped him develop some of these. Now he was also interested in using the moon rather than using satellites, but using the moon for moon bounce. So you can reflect signals from the moon, and he found that it was possible to do that, but it used to need a lot of power and very high gain antennas. It's not the sort of thing that an ordinary person could do. But he invented these digital modes, which made it possible to use much more modest antennas to progress with moon bounce, for example. So now instead of we're using higher frequencies to get you to use lower power, but we're also using digital modes of communication, and we can use lower power because we're using digital. Okay, digital communications enables us to use lower power, and one of those is something called the weak signal propagation reporter. That's something that I've been using. But this work, he's done this with cooperation from Princeton University. So this is not just some sort of amateur venture. This is a proper piece of research through Princeton University by a Nobel prize-winning physicist. So looking at big data and propagation, if we use the weak signal propagation reporter mode, or WSPR, you would set up a beacon station. You'd use low power, typically between 100 milliwatts and 5 watts. Well, those powers will give you propagation easily between the UK and Australia on a pretty regular basis. And it transmits about once every 10 to 20 minutes, depending on when you set it to transmit. The transmission normally lasts about 2 minutes, and it will transmit your call sign, the station call sign, and a position locator. So it won't transmit it as latitude and longitude. It will transmit as a 4-digit square locator, 4 or 6 digits. And the receiving stations, when they're not transmitting, will receive for 2 minutes and then decode the signals at the end of the 2 minutes, and they will then upload those signals, that will be the call sign and position locator, along with the signal strength that they've received your signal at, to this whispernet.org website. So all of those stations will be running the WSJTX encoder decoder software and reporter. Now that will automatically take care of the transmission, so whenever you set it to transmit, it will transmit at regular intervals. And you can also set it to do some band hopping from one band to another, it will also decode the signals and upload them automatically to this website. So what does a digital communication system look like, capable of sending and receiving WSPR data? Well, obviously you need an HF transceiver connected to a reasonably good antenna. You also need a computer and a data interface. Now most modern HF transceivers have a data input and output, and they also have what we call a CAT interface, a computer-aided tuning interface. So when receiving, the data output from the transceiver is fed into the data interface and converted into a format suitable to be fed into the line input interface of the sound card on the PC. And then when transmitting, a high-pitched tone is fed out of the speaker output of the sound card of the PC. That's fed into the data interface, and then that is then in turn fed into the data input of the transceiver. Now this high-pitched tone just sounds like a tone, but it's actually being modulated. It's using frequency shift keying, but the change in frequency is so subtle that you don't really notice the difference. It doesn't sound as if the frequency is changing at all. Now obviously from the USB output of the PC, that's connected to the CAT interface of the transceiver. That will enable us to change frequency when we need to, and also switch between transmit and receive. So this is the WSJTX software, and so if you look at the display at the top there, you've got the time in UTC as the first column. You've got the signal strength in dB, the second column. Don't need to worry about the next column, but it's the frequency. You've got the frequency of the received station, and if you move over towards the call sign, you've got the call of the received station, and the grid is actually the position as a grid square. It's either 4 or 6 digits. And then to the right of that, you've got the power output in decibels per milliwatt, or dBms. And then the final column on the right is the distance between the receiving station and this call sign in kilometers. So if we start with the first row, you can see that at 0342, a station with a signal strength of minus 24 dB was received. That's relatively weak, but it was received on a frequency of about 3.57 megahertz. The call sign was HB9DOZ. I know that's from Switzerland actually, and the grid square was JN37. The power output was 23 dBms. That's actually only about 200 milliwatts in actual wattage terms, so that's actually quite a good result there for that station. And the distance was 721 kilometers. And you can see in the other rows that a number of other stations were received, mainly from within Europe, on the 3.5 megahertz band. And then at 0344, just above the dotted line there, you can see that on the 5.288 megahertz frequency, a signal was received from a call sign of OZ2JBR, which is actually a Danish call sign, and they were running 37 dBms, which is about 5 watts output, so it's a bit higher power, and at a distance of 1,097 kilometers. Then at 0348, my station is transmitting on the 30 meter band, just doing that for that will be transmitting for 2 minutes. And then at 0346, another 3 stations were received on the 7 megahertz band. The first of those is EA8DBU, that's from the Canary Islands. And the next 2 are American stations, so you can see that you've got WA3DNM received from a distance of 5,665 kilometers. And the station below that, AC1LL, that's only using a power of about 1 watt at just under 5,000 kilometers, so that's pretty good going. And I've got the transmitter enabled, and in fact on this this readout here, you can see that I'm transmitting on a frequency of 24.9 megahertz approximately in the 12 meter band, and my power output is, if you look down the bottom right there, is 37 dBm or 5 watts. And if you look further down, you can see a green bar, and you can see that it's, next to that you've got 69 out of 120. So I'm just over halfway through the 2-minute transmitting sequence on this 24 megahertz frequency. I've got band hopping enabled, so this is actually switching between bands. It's transmitting on one band, then listening, and then switching to another band and listening and transmitting, and then switching to another band, and so on. And that's the way the system basically works. Also in the WSJTX program, you can view the received radio signal spectrum. Now within a 200 Hz bandwidth, or a fifth of a kilohertz bandwidth on each band, all stations that are transmitting at their allotted time will send for 2 minutes. And what you can see here is each of those reddy orangey lines represents 1 or 2 stations that are transmitting currently. So at the top there, we're looking at the 20 meter band, and there are currently 3 or 4 stations transmitting in this time slot. Underneath that, you can see the 40 meter band. You can see there are quite a few more stations transmitting on 40 meters. Below that, you can see the 15 meter band, where we listened for 4 minutes in total, two listening periods, and there were no signals that were apparently received then. And below that, you can see a single station being received on 17 meters, and so on. The red line that you see there represents the time when my station was actually transmitting. So it's actually useful to look at the spectrum and to view the received stations. So this received information is uploaded to the WhisperNet website, and it's stored in a database, and you can view the database, and you can see here that we're looking at an example from a sample from the 20 meter band, And if you look at the columns in the display, the first column is the date, and then you've got the column to the right is the call sign of the transmitting station. Then you've got their frequency. Then you've got the signal to noise ratio, or the signal strength that that station was received at by a reporting station or a receiving station. Then you've got the grid, that's the position, either a 4-digit or 6-digit grid locator in the next column. Then you've got their power expressed in dBs per milliwatt and in watts. And then you've got the reporter. So this is the station that received them. And you've got their call sign and also their locator as well. Then you've got the distance between the two stations in kilometers and in miles. And the mode that we're using is called whisper. So if we look at the first row there as an example, on the 14th of November at 23:06, the call sign K5SWA transmitted. They transmitted on a frequency of just over 14 megahertz. A receiving station received them with a signal to noise ratio, received strength that is, of -12. Their grid was EM12OX, that was their position. They were transmitting with a power of 5 watts, and that was received by the call sign KA7OEI. They've also got a locator square, and the distance between the two stations was 1591 kilometers or 989 miles. And you can see there are a number of entries. Yeah, there are several rows there with different stations and received by different receiving stations at different distances as well. So this data on the WhisperNet website can also be represented in a map format. So you can see these little red markers on the map of the world there, and each with their own call sign. And the lines drawn between them represent at one end of the line will be a transmitter, a station that's transmitting, and at the other end will be a station receiving that signal. And so there are hundreds of stations all over the world. Even in Antarctica, you can see that there's a station right at the bottom of the screen there with a call sign DP0GVN, and they're a German Antarctic research station doing propagation studies from Antarctica. And you can see that at the moment they're receiving signals from Europe and also North America. So it's a truly global project involving hundreds of sending and receiving stations. So this propagation data is uploaded to the WhisperNet website. There's data available for almost 14 years. As you can see here, it's archived every month for the last 14 years. And you've got 2008, March, April, May, etc. It's archived as a gzip or a zip file. There's several gigabytes of data for each year because there are several hundreds of stations taking part, and they're uploading every few minutes to the WhisperNet website every day of the year for year in, year out. So there's a lot of data. It's big data, and you could use this as part of a research project to analyze the data. Perhaps it could be used to better inform research into solar activity, but it is being used to better inform worldwide propagation prediction research, and obviously it's used by software such as the VOACAP software to better inform their prediction capabilities of the software. So this is a map of the activity at my Whisper station taken from the WhisperNet website over about a 12-hour period on one particular day in November. Over on the left-hand side you can see that I'm sending and receiving the stations to and from North America and also South America as far as Brazil. I'm also being received by the German Antarctic Survey Station in Antarctica. There are a number of European stations receiving me as far away as Iceland, and over on the right hand side you can see that I'm being received by a number of Australian stations and also a shortwave listener from New Zealand. So it just shows that with just 5 watts to a simple wire antenna that you can get a really worldwide coverage. Now this is just a section of the database from the WhisperNet website that I retrieved relating to signals that other stations received from my station. And I thought this would be quite useful to illustrate perhaps why it was thought that HF, high frequency, was originally thought to be useless. So if you look at those red circles there, you can see under the column SNR, which is the received signal to noise ratio, or the relative signal strength, that the first red circle is minus 28. So that's very weak. It means that that signal is just on the borderline of readability. Then if you go across to the right there, you'll see that was received by a station with a call sign of G7ELK. That was received from my station. And you can see over on the right hand side there under distance that he's just 11 miles from me. So he could only just barely make out my signals 11 miles away. Now go down to the next two lines below that. You'll see there's another red circle under SNR. It says minus 26. That's slightly stronger signals received from of my station. And go over to the right and you see the reporter has got a call sign of VK4CT. Go over to the right again where there's a rectangle and you'll see that the distance is over 10,000 miles. So actually that station in Australia is receiving me. My signals are slightly stronger in Australia than they are 11 miles up the road. Okay, and then if you go to look at the blue circle above just the second row where it says +1 and then go across to the right, you'll see the call sign DJ9PC. That's a German station. And going over to the right, you'll see he's got a distance of 569. Now, a positive value means that the signals are quite strong. So I'm being received in Germany much stronger than the signals that I'm being received 11 miles up the road. Okay, so that just shows you perhaps why it was thought that high frequency was thought to be useless originally, until they started exploring further afield. So that's really the end of my presentation. Thanks for listening, and I hope that you found it interesting, and I hope you found it useful in seeing that the types of software that's available from this very useful piece of software, the VOA cap, and the many things you can do with it, and also how that you can use these digital modes for gathering big data, which is of relevance, of course, to computing. And perhaps I'll hand it over to you for questions.